All right, so hey, when you're doing the problems, no need to reconstruct these division functions, okay? These 6 pages of notes prove that we derived them. So when you're doing problems and they say, hey, you're working with a whatever, critically damped system, start with the equation. Okay, that's why we do it. All right. All right, where were we? Okay, so that covers what we're going to do in 3.4. Now, a subsequent section, so they talk about force and external force being applied. Now, what we did was we ended up with a homogeneous equation. That's when there's no other external force. We're going to stick with that. In a further section, 3.6 I think it is, then they consider this mass spring system with another external force. And we're skipping that. We're going to skip that section. It was optional on our syllabus anyway. In the back of my mind, I knew extra time. Okay. Yeah. Spare time. So we're gonna skip 3.6. And that results in a non-homogeneous equation. However, we are going to be looking at linear nth degree, but linear differential equations that are non-homogeneous. Okay, we're going to look at how to start solving those as well. Anyway, we're just not going to then apply it to this mass spring system. Okay, so that does bring us to section 3.5. We're going to start looking at those non-homogeneous equations. All right, so section 3.5, non-homogeneous differential equations. All right, and we're going to look at, first of all, and we're going to see where we get today, but the method of undetermined coefficients. Okay. So, in the case of a non-homogeneous linear differential equation, so this is the form, nth derivative, so it's an nth order equation, plus, and these functions, p sub 1 of x, y sub, or not sub n minus 1, but n minus first derivative plus dot dot dot. And non-homogeneous means we have some non-zero function on the right. Okay. We do retain that sort of terminology that this is sometimes referred to as a forcing function. Okay, from this, I think. Okay, so call this equation 1. All right, So in the case of an equation like that, we just did talk about the theory without a proof. But if we have a linear, non-homogeneous equation like this, then the general solution can be written y of x equals y sub c plus y sub p, where y sub c represents the complementary function, c sub 1 y1 plus c2 y2 plus c sub n y sub n, which represents the general solution of the associated homogeneous equation, the homogeneous equation associated with this guy. So this is our complementary, that's what the C is for, complementary function. Plus y sub p. And y sub p, if we can find it, is just one particular solution to the non-homogeneous. Okay? So basically we could just append the general solution to the homogeneous equation, just tack on one particular solution to the non-homogeneous, the original equation, and that is the giant solution for the non-homogeneous equation. All right, so some things to note. We've already talked about the process of finding the complementary function. So this represents the solution to the homogeneous, the related homogeneous equation. You should stop it there. Abbreviate it there, homogeneous equation. Okay. So some notes. We've talked about how to do that. So y sub c, it represents the general solution to the associated homogeneous equation. So by considering y n minus 1 And remember how we do this, we take, if it's linear or constant coefficients, we take y to be e to the rx and solve. Okay? And hopefully we can find those n linearly independent solutions, and we tack them all together, and that's our general solution in what's called our complementary function. And when we're searching for the general solution. Okay. Now, the next step is we want to try and find a particular solution. And the method of undetermined coefficients is just a glorified guess and check system. Okay. Glorified in that, well, it's not just random. We'll make some educated guesses. So we find y sub p by making an educated guess. All right, so we sort of assume that y sub p is of the same general form as the forcing function f of x. Okay, and we'll talk more about what that means after we do some examples. But it's going to be a times something. If this is a third degree, sorry, this is too zoomed in now. If f of x is a third degree polynomial, then we would take y sub p, start with the guess that y sub p is a third degree polynomial, and attach on all its terms. So a times x cubed plus bx squared plus cx plus d okay? Assume that it takes on the same form as f. So these just represent some terms. Same form as f. Of course, as with everything else, there are exceptions, but we're going to start with doing some of this educated guesswork. So same form as f of x and its derivatives. We want to include any terms that may appear as the derivative of f of x too. So if f of x is just x cubed on the right, its successive derivatives are x squared, x, and constant. Up to a scalar multiple out front, 3x squared, 6x, stuff like that. So we want to include all the forms of its derivatives as well in our guess. Okay? All right. So what I mean in this little parenthetical statement is, as long, oh, right, this is actually separate. Oops. Let's do a new page. All right. So once we guess this form of y sub p, we sub y sub p and its derivatives into equation 1. Okay. So we guess the form of the solution, put it in there, find all its derivatives, and then we find those coefficients, a, b, c, those constants that make the left and right hand side equal. All right, so we sub y sub p into 1 and find those coefficients. However many there are, a, b, c, whatever. Okay. And one other note. And we'll see what this means exactly. As long as no part of f of x appears in y sub c. So after we find the complementary function, that complementary function can't contain f of x. If it does, then f of x would also be one of the solutions to the homogeneous equation, and therefore will not solve the regular one because it will be equal to 0. We'll see an example of that. All right. So as long as no part of f of x appears in the complementary function, then we assume that y sub p is of the form of f of x and its derivatives. So, even in the book they say there's no proof for this because this is just a suggestion of the way to do of a procedure. I like that. This doesn't require proof if you read Rule 1, note underneath it. Note that this rule is not a theorem requiring proof. It is merely a procedure to be followed in searching for a particular solution. So let's go ahead and try this out, and hopefully it illuminates a little bit of what I'm talking about here.